Hello once again, Mr. Wakefield here, looking at section 4.3 now. And logarithmic functions, our first introduction into logarithmic functions, log functions for short. A lot of people just call them logs. What are they? Okay. Basically, where logs come from is it's a combination of what we've done in the last couple of sections. As you see here, I'm putting a piece of scratch paper on the screen. I want to show you something. You don't have to write this down, although you certainly can if you want. But in section 4.1, we talked about inverse functions, and in section 4.2, we talked about exponential functions. I'll just take an example here. Say I looked at 2 to the x. That was an example of something we looked in 4.2. Suppose I wanted to take the inverse of that. All right. What I did in 4.1 to take an inverse of anything is I first of all changed f of x to y. I then interchanged the x and the y, like this. And then after that, I then got y by itself, and then whatever that new y was equal to would be your inverse function. Well, the problem with that is that how do you get a variable by itself when it's stuck inside of an exponent? We kind of saw a little bit of that in the last section, but that's really not going to work here because the 2 and the x, you can't really get a common base right there like we did in the last section, mainly because the x is a variable and the 2 is not, all right? There's other reasons too there, but we're kind of stuck here. And so what I believe mathematicians long ago, when they came up with logs, is they said, hey, we need to figure out a way to get the variable out of the exponent here and get it by itself so we could solve for it. All right, so what they came up with was this. They said y, which is the exponent, that's very key here, you guys. The y is the exponent, and the y is equal to log. And then next to the log, what you do is you take the base. The base here is 2, and you put it. You don't put it on the same level as the g. You drop it a little bit below the g there. That's how you write the base. And then whatever the answer was when you took the base and the exponent together, whatever it was equal to, which in this case is x, that is what I like to call the product term. All right. That is on the same level as log. It's next to the 2. Again, don't put it at the same level as 2. Bring it back up to the same line as the log there. That's just how you write it. But let me just make sure you understand what we just did here. Okay. Whenever you have a log, all right, again, the thing underneath the g, that is the base. The thing that is the base and the exponent together, what it's equal to, that is this thing that goes next to the base in the log statement here. All right. And then the entire logarithm is equal to the exponent. Let me say that again. I'm going to say it a lot, but logarithms are always equal to exponents. Logs are exponents, you guys. What exponent? It's the exponent you get when this is your base here, and this is your answer or your product term, as I like to call it, when you take the base and the exponent together. So, for example, if I said this right here, and I said, what is that thing equal to? What they're asking, you guys, is they're asking 3 to what power is equal to 9? Remember, logarithms are equal to exponents. So if they say, hey, what is that thing equal to? This is what they're asking. 3 to what power, because the logarithm is the exponent, and so that's what they want to know. 3 to what power is equal to 9? Well, we know that 2 is the correct exponent right there because 3 squared is 9. And so therefore, a log base 3 of 9 is equal to 2. Okay? The base goes here. The entire logarithm is equal to the exponent. And then the thing that goes next to the base, that is what the base and the exponent together are equal to. 3 squared is 9. That's how logarithms work. All right? So let's talk about that a little bit more. But basically, just before I go on, though, right now, notice that we just found the inverse. All right? We interchanged the x and the y. We then got the new y by itself. So that means, you guys, that logarithmic functions, that's a tough word to say sometimes. Logarithmic functions are inverses, the basic logarithmic functions like this, are the inverses of these functions, the exponential functions from section 4.2. All right, that'll help us out with some things we're going to do later here as well. And so let's go ahead and take a look at some examples here. It says evaluate each logarithm, meaning just figure out what it's equal to. All right, there's no variables here. You just figure out what number is this thing equal to. Again, what are they asking for here? They're saying that the 3 is the base. The 81 is the answer that you get when you take the base and the exponent together. And then since they're asking you, hey, what's the logarithm equal to? They're asking for the exponent. They want to know what this exponent is. All right, so here's what you do. We do what we did basically in the last section. Let me just pull that out in front of you here for just a moment. Okay, if you have a base and an exponent, and we do here, okay, I know I put a question mark right there, but that's similar to having an X right there because we're trying to figure out what the question mark is equal to, just like we want to know what the X was equal to. Okay, so this is similar to having 3 to the X power, okay, but you have a base and an exponent here, just like we did here, and then just a single number on the other side. So what did we do in that case here? We tried to make the 25 into 5 to a power so that we'd have a common base. Let's do that same thing here. Do we know what 81 is as far as 3 to a power? Yeah, we do. It is 3 to the 4th. 3 to the 4th is equal to 81. All right. And so now I have that same thing that I had in the last section where I'm trying to get it to look like this right here. All right. And this is what we can typically do when we have when they ask us to evaluate a logarithm. Try to get it to look like this, and then that'll help you find the answer. Because what happens, as you guys know now from the last section, the 3's cancel when it's written like this. And so we get question mark is equal to 4. In other words, you just have the exponents left. And so we just answered the question, didn't we? All right, we just found out that the logarithm is equal to 4 because the question mark was what we were trying to figure out there. Let's do that again here. All right, again here it says what? It says that 3 is the base again because remember the thing that's next to the G is the base. The thing next to the base is what the answer that you get when you take the base and the exponent together. And then because they're asking for the logarithm, they want to know what is this exponent that goes with that base to equal 1/3. Okay, here's what you do when you have a fraction. All right, try to, and in particular when you have a 1 on the top, what I'd like you to do is try to take the bottom and try to make that the same base as this over here. And then we'll eventually make it look like this formula here again. But start out with the bottom and then we'll go from there. As you guys know, that's the same thing as 3 to the 1st on the bottom. And again, I want to make it the same base as this over here, 3 and 3, right? Okay. So 3 question mark 3 to the 1st. Okay, the reason why I did that is because we know that, as we've talked about in the last section and before that, when you have 1 over 3 to the 1st, that is the same thing as 3 to the -1, isn't it? Okay, isn't that true? From we learned that formula again. We were reminded of it in the last section. Let me write it down again. A to the -n is the same thing as 1 over a to the +n. All right, so 3 to the -1, 1 over 3 to the 1st. So that means that we have 3 to the unknown power right there, just bringing that down, is equal to 3 to the -1. Now that it looks like this right here, now that it looks like that, 3 to the question mark is equal to 3 to the -1, we now know that the question mark is equal to -1. Because we can cancel out the 3's when it's written like that. And so our final answer there is -1. Okay. Next one. When you have a decimal, you guys remember how to read decimals so that they look like fractions? Let me show you what I mean. This is 0 and 1/100ths, and I say that because this is in the hundreds place. Remember, this is the tenths place right here. This is the hundreds place. If you had another digit, it would be the thousandths place. And so when you have 0 and 1/100ths, that is the same thing as it's just like it sounds. 1/100ths is 1 over 100. Okay, just like 1/3 is 1 over 3. 1/100ths is 1 over 100. Okay, so it ends up being very similar to the last problem. Let me set it up here though. What do we want to know here? We want to know 10 to what power is equal to 1 over 100. Okay, 10 is the base because it's next to the G. The decimal, which is the same thing as this fraction here, same thing, is next to the base, so that's the answer you get. All right, now we just want to know what the exponent is that will make that all possible. All right, so just like in the last problem, all right, if you've got 1 over a fraction here, the easiest way to do this is to try to take the bottom part here and try to give that a common base of 10. All right, and then we'll do that thing with the negative exponent like we did in the last problem. I'll show you that again. So we have 10 to the question mark is equal to 1 over 10 to the second. Okay. And just like in the last problem, 1 over 10 to the second is the same thing as 10 to the -2, right? Just following this formula, 10 to the -2, 1 over 10 squared. Okay. So now that it looks just like this formula, again here, A, B, A, C, all right, I can drop the A's, I can cancel those guys out, and I get question mark is equal to -2. So again, the final answer now is -2. Let's keep going here. When you have a radical, all right, how do we deal with that? Let's talk about that. But what do they want to know first of all? They want to know 6 to what power is equal to square root of 6. Okay. Well, remember, we ultimately want to take both, we want both sides to be a base and an exponent, right? Well, how do I do that with a radical? Well, we learned that radicals are directly related to fraction exponents. All right. When you have just a radical without the bracket and the exponent on the outside, how do we write that? Okay, for example, here was a good example here. When you have just a radical, not including the -1 here, don't pay attention to that, just a radical right here. Okay, how do you write that? If it's just a radical, the numerator is automatically 1 when you set up the fraction exponent, and then the index number becomes your denominator. So 4th root of 16, all right, is 16 to the 1/4. All right. In the same way, what is the square root of 6? Since the index number is 2, it's an invisible 2 right there since it's a square root. Wouldn't this be a denominator of 2? And again, when it's just a radical, the numerator is 1. And you don't have like that outside bracket, the bracket and the outside exponent. Okay. That's just if you have just a single number on the inside. Okay, there's other ways to do it if there's a base and an exponent in there. But if it's just a single number in there and it's just a radical without that other stuff, the bracket and the exponent outside of it, then the numerator is definitely 1. Don't worry about that. And then the denominator is just the same as the index number. Okay. And so then that reveals to us everything we need to know, right? Because now we got it's written like A, B, A, C. We can cancel out the 6's, and our final answer is 1/2. All right, so 6 to the 1/2 power, all right, is equal to square root of 6. All right, that's exactly what they're asking for here. E to what power is equal to 1? Okay. at least for the bases that we're going to be doing in this section, including or in any logarithm problem, including this one here with base e, the only way you can get an answer of 1 when you set it up to be base and an exponent, the only way to make that happen in this case is to have an exponent of 0. That's the only way to get 1. All right, at least with the bases that we look at whenever we do logarithms, which is the same as the exponential function. You're just looking at bases that are positive and not equal to 1 either. Okay, so in that case, the exponent has to be 0 in order to get this equal to 1 here. And so we did it again. We made it look like this right here. All right, the e's cancel, and we get an answer of 0. So the lesson learned here, you guys, and I'll review this here in a moment. The lesson here is that whenever the product term is equal to 1, the answer for the logarithm has got to automatically be 0, because that's the only way you could have any base, at least any base we're going to look at, to a power equal to 1. The only way that could happen is if that power, that exponent, is equal to 0. That's the only way. Lastly here, 3 to what power is equal to this whole thing right here? Well, again, this kind of looks like a problem that we did in right here a little bit, where you're trying to get a common base. We have a base on each side already. We got 3 to a power. We got 27 to a power. But isn't it true that 27 can be written with a base of 3? Isn't that 3 to the third? So these are the types of things you need to be looking for here. You got to say, okay, is 3 to a power equal to 27? Is 27 to a power going to be equal to 3? Can I convert one of those two bases to be the other one, to be equal to the other one? Yeah, we can. 27 is equal to 3 to the third. But remember what we talked about. If you have a bracket, we saw this in this E problem here in the previous section. If you've got a bracket with an exponent on the inside and then another exponent on the outside, we need to get rid of that bracket so that it's clear exactly what my one exponent is going to be equal to. So I do that just like I did in the last section by multiplying those exponents. 3 times 3 halves is what? 3 times 3 halves is 9 halves, isn't it? 9 halves. And so we get 3 to the 9 halves power, okay, is equal to 3 to the question mark power. So now that's what? That is, again, it looks just like the ABAC thing again. So now we can get rid of the 3's, and then it's clear what the exponent's equal to. It's equal to 9 halves. It's clear because the question mark is now by itself. Just like if it had been a variable, you wanted to solve for the question mark so that you know what that missing question mark was equal to. Just like when you get x by itself to solve for x. You get the question mark by itself, we got it by itself, and now we know exactly what that missing exponent is. It's 9 halves. All right. So that's the first 6 problems right there. Now, a few of the things I want to, or next thing I want to look at here is just on the front here real quick. We already talked about how when, there's just some properties I need to get you familiar with here. We already talked about the fact that when the product term is equal to 1, no matter what the base is, that's why it has a little b right here. The b, the little b is implying that it could be any base at all. Any base at all, if the product term is 1, the logarithm, the entire logarithm has to be equal to 0. Okay. Next one here. This is saying here that if the base and the product term are both exactly the same, then the exponent's got to be equal to 1. Why do you think that's true? It's true because we know that a logarithm is equal to an exponent. And in particular, it is the exponent that you get when you take this is your base and this is your answer. So I put the base here. I put the answer, which in this case is the same, over here. Isn't it true that this has got to be an exponent of 1 in order for this to be true? B to the first is equal to B, right? And so that's the reason why when these two things are the same, b and b, then the logarithm has to be equal to 1. Okay, let's do that again here in the third property. Again, these are properties that you want to know here for a number of reasons, as you'll see coming up. But I want you to, I don't want to just tell you to just remember them, okay, or memorize them. Do that, but also understand why they're true. There's a better chance you remember them long term if you remember why. So why is this one true? It's because, again, the base is b. The answer is b to the x. All right. When you have just a base and an exponent right there like that, I just want to make it clear that's all supposed to be the product term. The x right there, you're not taking the entire logarithm to the x power. It is just when you have a base and an exponent next to your little base underneath the g right there, this thing right here, that is all meant to be the product term. It's all meant to be the answer. All right. The bigger b is being taken to the x power, not the entire logarithm. Just the bigger b is when it's written like that. I just want to make sure you understand the language of how it's written there. So what do we got? We've got b is the base, bx is the answer, and then they say, oh, okay, what is the missing exponent? Well, you know that, again, when it looks like this with the common base, you can get rid of the b's, and that means that question mark is equal to x, which then means that the logarithm is equal to x, and that's why it says x right there. Okay, so I just wanted you to understand how those first three properties work, where they came from. This fourth one's a little bit tougher to explain. I'll skip the explanation. I just want you to memorize that one. It'll probably just be easier that way. But notice that the b here and the little b inside the logarithm is actually inside the exponent here. But if the little b and the big B are the same, then the thing that's next to the little b will always be your answer. Always, always, always. But those two things have to be the same. Okay, and if they are, then that's all you got to do is just say that that thing next to the little b is your answer automatically. All right, so that's an explanation of those four properties. We'll talk more about these other properties down here in the next section mainly, but I wrote them down here as well, but don't worry about those yet. All right, so. Okay, guys, notice in this next set of problems here, we have equations with logarithms in it. And in particular, with the exception of number 11, which I'll cover in a little bit, you have a logarithm along with its base and its product term all by itself. I want to make something perfectly clear here, you guys. It's really important before we move on. Okay, no logarithm can stand by itself. If I just write down... let me pull out a piece of scratch paper again. Here it is. If I just write down the word log all by itself, that means absolutely nothing in a math class. Nothing. Okay? It may mean something in an English class, like it's short for log cabin or log whatever in English, but in a math class, that means nothing. Okay, you cannot write down the letters LOG without having what also? You need to have the base and the product term, okay? Without those two things, the base and the product term, all right, the log means nothing. So don't ever write down log by itself, okay? So if you end up with something like that in your problem, you did something wrong, okay? You should always have a base and a product term. Now, there is one exception to that. Sometimes the base is invisible. For example, if I wrote down log 100, notice I have the product term there, but the base is invisible. When that happens, the base is still there. It's just that when it's invisible, that means that the base is 10. We'll get into that more in the next section. You don't need to worry about that yet. But every single log definitely has to have a product term. Okay, it should also have a base. It's just that sometimes it's invisible. So if you don't write down the base, you guys, it had better be equal to 10. Otherwise, you did something wrong. Okay, because when it's invisible, it needs to be 10. All right, but don't ever just write down LOG by itself. I just want to make sure you understand the the overall thing that the word or the letters log mean. All right. You can't have, because remember, what is a log again? A log is an exponent. But you can't have an exponent without what two things? You can't have an exponent without having a base and an answer, a product term, in other words. You can't have that exponent without those other two things. And so log means nothing. Since a log is an exponent, it means nothing without its base, which in this case is an invisible 10, and its product term, which is the answer. All right. That's why you can't just write down log by itself. All right. You've got to at least have the product term, and then if you don't write down the base, that means it's 10. All right. So just want to clear that up. But when you have a log along with its base and along with its base and product term here, and that's all you have is just those three things. Okay. The way you solve that equation, all right, when you have the log and the base and the product term all by itself on one side, is like this. You take the 3, the base, and then whatever the entire log is equal to, which is x, that becomes your exponent because logs are equal to exponents. And then the product term, remember, is the answer. Do you see how I'm just doing the same thing that I did up here in the first 6 problems, where I'm taking the base, and it becomes the base here. I'm taking the product term, it becomes the answer. But instead of putting a question mark there, because we didn't have an equation here, the log wasn't equal to anything here yet, so that's why I put that question mark here. This time it's equal to something. It's equal to x. So instead of putting the question mark there, I put the x there. That's really the only difference. Otherwise, it's the same kind of thing that's going on up here. All right. Whatever the log is equal to, that becomes your exponent. All right. Then what I have now is I have an equation, once again, where I have the variable and the exponent, just like I had in the previous section. Once again, we're seeing this a lot today here, where you have when you have a variable and an exponent, you at least want to try. And later on, we'll have to take an alternative measure because it won't work. But right now, you need to at least try to get it to look like this. And we can do that here because we know that 81 is what? 81 is 3 to the 4th. Okay, just like 100 was 10 squared, and so I tried to make it a common base right there. Same thing with the 81. I make it a common base with this one over here. And then I know what? I know that 1 over 3 to the 4th is the same thing as 3 to the negative 4. And so I converted the fraction to 3 to the negative 4. Now that it looks like that ABAC thing again, what do? I cancel out the 3's and I get negative 4. X equal to negative 4. So this is what you do when you have, again, what is the requirement here in order to do that? You need to have the log by itself. If there's anything else on this side of the equal sign besides the log and its base and product term, then that's different. And we'll see problems like that later. You don't need to worry about that yet. Okay. So what is this telling us when we've got the log by itself equal to something over here? It means that x is the base because it's next to the g. The product term is 27 over 64. All right, so that's going to be what the whole thing's equal to. Just like up here, the product term is always what it's equal to. And then the entire logarithm is equal to the exponent. So that would be x to the 3rd. Okay. And then you solve this equation. How do I solve that equation? I solve it by, let me pull out it's actually right here. Remember we said that when you have a x to the 3rd, because 3 is an odd number, x to the 3rd equal to 27/64. That means that x is going to be equal to the cube root of 27/64. I'm just using this rule that I learned in the last section. All right. So this is going to be x equal to cube root of 27/64. Okay. And so we did it. We got x by itself. I just need to figure out what this thing is equal to if I can, and I can because 27 and 64 are perfect cube numbers, all right? We know what is being cubed to get 27 and 64. This is 3 to the third, and this is 4 to the third. And so therefore, the answer then is 3/4. Because if I cube 3/4, all right, if I take 3/4 to the third power, it's going to be equal to that fraction. All right, let me show you that. So if you know, if it's a cube root problem and you know what these two things are, what two numbers are being cubed there to get these two numbers, that's going to form your fraction there. All right. And since it's cubed, you don't have to worry about making it positive like if it was a square root. All right. It's just whatever works is going to be the answer. And so it's 3/4. All right. Next one. Again, the log is all by itself. The log, the base, and the product term. That's all that's there on that side of the equal sign. So we can jump right into the next step here. The base, the product term, and then the exponent is what the entire logarithm is equal to. Log is equal to x, so the x is the exponent. Okay. Once again, we now have, unlike the last problem, I want to make this clear, you guys, you do not do the A, B, A, C thing when the variable is in the base. It's when the variable is in the exponent. That's when you do this property. Some of you might have been wondering that. I understand that question. I'm glad we're addressing it. All right. It's just when the variable or the question mark, okay, because the question mark is like a variable. We're trying to solve for it. It's when that thing is in the exponent, not the base. That's when you use this property, or at least try to. Okay, at least try to. And we can here because we know that just like with the square root problem up here, okay, got it right here. We want to try to, since this is 7 here, we want to try to make a base of 7 here. And when it's a radical, we can convert that to a 7 with a fraction exponent. Remember, when it's just a radical, the numerator, as long as it's just a single number on the inside there, like the 7, the numerator of the fraction exponent is then going to be 1. And then the 5, the root number, that's your denominator of your fraction exponent. Okay, just like this was 1/2 because it was a square root. Because this is a fifth root, it's just the same thing except for it's a 5 on the bottom instead of the 2. Because it's not a square root, it's a fifth root. Now that it looks like the whole A, B, A, C thing again, okay, because it looks like that, what do? We cancel out the 7s, and there's your final answer. Let's keep going here. Number 10. Again, you have a logarithm all by itself, including its base and product term, of course. Okay, because no logarithm can be without that. But if those three things are the only things you have, let's jump right into it. What do we have? The base is 2. The product term is x, because that's next to the base in the logarithm there. And then the exponent is equal to 3, because the entire logarithm is equal to 3. And so we did it. We got the x out of the logarithm there. That's our goal here, is to get the x out of the logarithm if it's stuck in there. All right, but anyway, because it's x is already by itself, all we got to do is figure out what this is equal to, and we're done. We don't have to get x by itself. It already is. And as you guys know, 2 to the third is 8. So if you've got a constant base and a constant exponent, please don't leave it like that. Actually figure that out. Okay. And that's why we got 8. Especially if it's two whole numbers there, okay? Like 2 to the third, or 3 to the fourth, or 4 to the second, something like that. Figure that out. This problem is different, you guys. All right. I'm going to skip that for a moment and go, and I'll come back to it after I do number 12, because number 12, again, is a logarithm along with its base and product term all by itself. All by itself. And so, again, rewrite it so that the base is now written as a base, not stuck inside the logarithm, but it's written as a base. The product term is 16 because it's next to the base. And then the exponent is what the entire logarithm is equal to, x to the negative 2. How did we learn in the last section about how to do equations with negative exponents when we're trying to solve an equation with a negative exponent? We did this right here, right there, where we, see how we had x to the negative 6, we converted it to 1 over x to the 6th? We can do the same exact thing here, you guys. We can convert this to 1 over x squared. All right. Anytime we have a fraction on one side, as we've seen in the past, anytime you have a fraction on one side, and that's it, nothing else, and then on the other side you just have a regular term, what you do is you make that term into a fraction also, and then you cross multiply. If I do that, I get 16 times x squared, and then I get 1 times 1. There we go. This is a quadratic equation, but in particular, because of the fact that I can get the x squared by itself without having a variable on the other side, that means that I can do the what? I can do the square root property that we talked about. We reviewed that in the last section, and let me put it back up here on the screen here for you. Just a moment. Just need a minute to find it here. Okay. Almost there. Okay. Fumbling through my stuff here. I apologize. But while I'm looking at that, remember, when you have a quadratic equation where you can easily get the x squared by itself without having a variable on the other side after you do that, then square root property is what you want to do. Just like I did here, I was able to get the x squared by itself without having the any variable on the other side. Same thing here in this current problem. If I divide out the 16, okay, I would get x squared equal to 1/16, wouldn't I? Okay, and that's what you do when you want to get something by itself. If it's being multiplied by something, it's just like having 16y equal to 1. If it was 16y equal to 1, you divide out the 16 to get the y by itself. It's the same thing here. All right, 16x squared, you divide out the 16 to get the x squared by itself. All right. What did we learn when we have x squared equal to a constant? We have, and I'm just going to condense it down here because I'm kind of running out of space here, but we know that when you have x squared equal to a constant, we reviewed this in the last section, and we also did it here in section 1.4, x squared equal to a constant, you have the double square root. And then after I simplified it, I put in the plus minus because the two answers are exactly the same, except for you had a plus in front and a minus in the front. It's the same thing here. All right, it's going to be plus or minus square root of 1/16. But what is the square root of 1/16? Because of the fact that 1 squared is 1 and 4 squared is 16, it's going to be 1/4, isn't it? All right, 1/4. Okay. So that's what happens when you have an equation with a log all by itself on one side. Okay, with a variable in it. No, actually, the variable doesn't need to be in it. Excuse me. But yeah, if you just have a logarithm on one side all by itself, along with its base and product term, that's what you do. Okay. In particular, I should also mention, if you have a log all by itself on one side, but you got some big humongous thing over on the other side, that could be a different story. That could cause you some problems. But if it's just a single term, like it was on all 5 of these problems that we just did, if it's just a single term over there, like -2 or 3 or x, then yes, this is the kind of method you want to do. If it's something really big like that, and we might run into that later, I'll explain that at that time. But if it's just a single term on the other side of the logarithm, this is what you do, okay? Last thing here, before we get to the graphs, is when you have this situation, you can see that the log is not by itself. The log is in the exponent, but then we have this base right here. So please do not do the same method that we just did here because the log is not by itself. However, the x is by itself, which is what we ultimately, that's our ultimate goal, is to get the x by itself. So that's good. We just need to figure out what this is equal to. Isn't that always true? If you've got x by itself, as long as it's not on the other side, if you've got x by itself, you just need to figure out what the other side's equal to, and you're done. And as I just showed you in the previous, let me flip this back over. That property where I said it's kind of hard to explain, but you just have to follow it here. If the b and the little b are the same, let me write that down here. 8 and the little 8. Okay, if we follow that same rule here, if we've got 8 here and the little 8 here, then this number next to the little 8 is going to be your answer automatically. So what's this going to be equal to then? It's going to be equal to 11, isn't it? Okay, because that's next to the little 8. And so, since x is by itself and it's not on the other side, you just have to figure out what this thing is. It's equal to 11 like we just explained, and that's all you got to do on that one. Okay, so that is number 11. All right, let's go ahead and move down here to the last 3 problems here, the graphing problems. And then notice it says in the directions that we want to graph each function using the same 5-step method we learned in sections 2.7 and 4.2. 4.2 is when we had the ones where the you had the variable inside of the exponent. And just to review that with you here for just a moment from 4.2, if you had, for example, 2 to the x or 3 to the x or 4 to the x, that's considered a basic graph, okay? And so if you had, for example, 2 to the x plus 2 power, then the x plus 2 would then be set equal to your old x values to figure out your new x values. We saw that. Let me go and give you a visual of that. Okay, you had when the exponent gets replaced by negative x minus 2, then negative x minus 2 becomes that thing you write down 5 times and all that. Same thing here, x plus 3 is the new exponent. You write that down 5 times, you figure out your new x values. All right, that's because the variable in the basic graph was the exponent. All right, well this time, with logarithmic graphs, this time the product term is the variable. So if your new product term in your problem is, say, for example, in number 13, it becomes 3 minus x, then that means that you're going to write down 3 minus x 5 times. Okay, and you're going to set it equal to the 5 old x values and solve those and all that stuff that we normally do. All right. But what are those old x values? They're not the same as before. They're not negative 2, negative 1, 0, 1, 2. Remember, logarithmic functions, you guys, are inverses of the functions that we saw in section 4.2, these functions. Now, that's going to help us here because remember, when you have inverses, the x's and y's switch. And so, see these y values that I have right here that I plugged into the function from here? And eventually you figure out what these are equal to. But the point is that I want you to realize something here. Instead of using these, since the x and y flip-flops when we go from one of these graphs to one of the log graphs, it would make sense that these values now right here that I'm circling are now going to be your x values that you start with. Okay. And that's not for every single log. It depends on what your base is. If the base is 2 to the x, then it would be this. If the base was 3, like if you had 3 to the x, then it would be 3 to the negative 2, 3 to the negative 1, 3 to the 0, 3 to the first, 3 to the second. And so in the same way, if you've got log base 3 of x, same thing. You're going to have 3 to the negative 2, 3 to the negative 1, 3 to the 0, 3 to the first, 3 to the second. If you had this one right here where the base is 4, again, it would be 4 to the negative 2, 4 to the negative 1 power, 4 to the 0 power, 4 to the first, and 4 to the second. It all depends on what your base is. So what you want to do is you want to do this right here, these 5 things, okay? And that's going to be your old x values when you have one of these log functions here, okay? Okay, so these are going to be the old x values that you're going to use for any time you have a log that you're trying to graph, okay? A function that has a log in it, all right? So, for example, in this current problem right here, it would be 1/3, sorry about that. There it is right there. It would be 1/3 to the -2, 1/3 to the -1, 1/3 to the 0, 1/3 to the first, and 1/3 to the second. Let's figure out what those things are, kind of off to the side here. All right, 1/3 to the -2 is going to be the same thing as this right here, 3 over 1 to the second power. Remember, you flip if you have a fraction taken to a negative power, you do this right here. All right, which we've done that a number of times here just in the last couple of sections, haven't we? And that would be 9, wouldn't it? 1/3 to the -1 in the same way. 1/3 to the -1 is going to be 3 over 1 to the first, which of course is 3. And so that's going to be the first two things that you're going to have up here, you guys. You're going to have 9, 3, all right, and then after that we need to do, so this is what 1/3 to the -2, 1/3 to the -1, 1/3 to the 0, like any 0 exponent is going to be 1. And then we have 1/3 to the first, anything to the first power is itself. And then finally, what is 1/3 to the second? Okay, well, 1/3 to the second, when you have something, when you have a fraction taken to a positive power, you just go 1 squared and 3 squared, don't you? And that would be, as you know, 1/9. 1/9. And so those are the 5 old x values that we have right here. Old x right there. Okay? Old x values. So, what are the new x values then? New x values. All right, again, you just simply solve for x right here. That means that we need to move over the 3 and then divide by -1. So moving over to the 3, we get 6. Divide out the -1, we get -6. Move over the 3, we get 0. Dividing out is still 0. Move over the 3, we get -2. Divide out and we get +2. Here's where it gets a little interesting. Like I've promised you before, when we're talking about x and y values that you put on a graph, you can change these to decimals, even if they're not exact and they're rounded up. That's okay. And we get what here? This would be 0.3. So if you did the same thing, we're going to get, moving that over, we get -2.7. But then when you divide by -1, it is +2.7. And finally, 1/9 is 0.1. If you move over the 3 and divide out, you get +2.9. All right. All right. The new y values. The new y values. Again, like always, when you do this 5-step method, once you get your new x's, you plug it into the function that you're, not the basic graph, but the final function here that you're actually trying to graph as the final answer. You plug these 5 x values, the new x values, into here, or into the function to get these new 5 y values. All right. Now, if I plug in -6, let me just point out something here real quick. When you plug something into a log where the variable is inside the product term, one other thing I need to point out even before that, excuse me, is when you have a parenthesis, you guys, next to the base, which is 1/3 here, when you have a parenthesis next to the base, the entire parenthesis is your product term. All right, that's why they put it in parentheses. So just want to make it clear, 3 is not the product term. 3 minus x is the product term. All right, so you got a bracket next to that. That entire bracket is your product term. So when you have a product term with a variable in it and you plug something into that, the first thing you need to do is you need to figure out what the product term is. Then you figure out what the logarithm is. In other words, the exponent. Okay, let's go through that carefully here. If I plug in -6, I get 3 minus -6, which is, let's write it down here. 3 minus -6 is 9, isn't it? So what they're saying is they're saying 1/3 to what power is equal to 9. All right. Well, we found out down here that 1/3 to the -2 power is equal to 9. And so that answer is going to be -2. All right. If I plug in 0, I get 1/3. I get log 1/3. Again, figure out the product term first. And 3 minus 0 is 3. So 1/3 to what power is equal to 3? You need to figure that out now after you figure out what the bracket is. All right, and that would be, as you can see here, the exponent is -1 down here. 1/3 to the -1 is equal to 3. And since logs are equal to exponents, that then means that this is equal to -1. Okay. And then how about 2? 2, you plug that in and you get 1. And anytime the product term is 1, this is going to be equal to 0. All right. I want you to notice a trend here that's going on. It'll make this easier instead of having to plug these things in. Okay, there's a trend going on here, and that is these numbers right here are going to end up being the same as the exponents that you plugged in originally. Okay, remember we said that we had to do 1/3 to the -2, 1/3 to the -1, 1/3 to the 0, okay, and so on. As long as you don't have something on the end of it here, see here we got the +2 on the end of the log, and then the +1 outside of the bracket now, because remember the bracket is a part of the logarithm. That doesn't count. I'm talking about behind that bracket. Unless you got the +2 and the +1 behind there, the answer for the new y values is just simply going to be the same as those original exponents that you used in order to calculate the old x values. In other words, it's going to be -2 to 2. -2 to 2. Okay, now if you do have something behind that, that's okay. That just means you're going to add 2 to each one of these numbers. Okay, you're going to add 1 to each one of those same numbers in that problem. We'll get to that in just a little bit, but that'll make it a little bit easier for you, all right, to figure this thing out for the new y values. All right, so that made things a lot less work there. And again, those decimals are not exact anyway, so that's going to throw you off if you try to plug those in anyway. So this is a nice little shortcut to that. If you plug in the fractions, you can still get it, but it's still tough because there's fractions there. So again, please do it this way. Mainly for that reason, when you get to the fractions and decimals, it's tough to figure it out otherwise. So, then what? Then we go ahead and graph these things. -6 and -2 is right here. 0, -1, 2, 0. 2.7, 1. And 2.9, 2. You can see that similar to this previous section, and it mentions this in the basic graphs anyway. Anytime you stem something off of a basic graph here, like we are doing right now, where the x gets replaced by the 3 minus x. Anytime you do that on one of these, you're going to end up with the same basic shape. It's just that, like we said before, when you go from a basic graph to the final graph, it'll still be the same basic shape, but it might be flipped over, spun around, okay, but it'll still be the same banana-looking shape. And so all the log graphs, since both of these graphs are banana-shaped looking things, that means that all of our log graphs will have that same banana shape. It's just that it's a matter of where is it, okay? Well, you can see here that a banana shape is starting to develop here, okay? But there's one more thing I want to do here before I graph this, and to make sure it's completely accurate. All right, we have an asymptote on log graphs also. Let's read this paragraph. It says, to graph a function that originates from one of the two basic graphs above, one of those basic graphs, follow the 5-step method as we talked about. To find the vertical asymptote. So this time, unlike the 4.2 graphs where we had the variable and the exponent, in order to find the asymptote, it's going to be vertical this time. Horizontal, in 4.2, vertical when you have a log graph here in 4.3. All right. So how do you find that vertical asymptote? You don't just look at the end of the graph, okay? Not like last time. Then we did that in 4.2. That helped us find that. In 4.3, it's totally different. What you do is you take the product term and you set it equal to 0. So, for example, if this was your problem right here, then you would set the x plus 3 equal to 0, like that, and then you'd solve that equation, and that would become your vertical asymptote right there, okay? Now, that's not the problem we're doing right now, but that's just an example. All right, so in this problem, we set the 3 minus x equal to 0. Sorry about that. So we set the 3 minus x equal to 0. We then move the x over to the other side to get it by itself, and then this is your vertical asymptote. And where is that vertical asymptote? It is right here. Again, like with any vertical asymptote, don't let the graph touch it, but make sure the graph gets closer and closer to it as it's going either forever upward or forever downward. We learned that back in 3.5. With a vertical asymptote, the graph's either going to get closer and closer to it as it goes forever upward or forever downward. Well, you can tell by the points here that we have that it's clearly going forever upward. It's not going to turn back around because then it wouldn't be a banana shape anymore. and it needs to be. So let's go ahead and graph this thing now, not allowing it to touch the vertical asymptote, but getting closer and closer to it, okay? And that's good enough right there. That'll get the job done there. All right, so let me go ahead and finish off this graph, doing my banana shape. Make sure that, like with all banana shapes, make sure it has arrows on both ends. Make sure that it is what? It is going up really fast on one end and down really slow on the other end. Or if it's flipped over, make sure it's the opposite. Make sure it's going down really fast and up really slow. But it's fast on one end and slow on the other. All right, as far as the up and down motion. All right, in this case, up real fast, down real slow. If you had a problem where the banana shape was flipped upside down, something like this, okay, then it would be down really fast and up really, it almost flattens out as you go up. So in this case, it would be down really fast and then it almost flattens out going up. But when the banana shape is like this right here, it's going up really fast and down almost in a flat way here at the end. So it's one or the other on those two possibilities. All right, let's try that again. These next two problems are quite similar, with the major difference being the 2 and the 1 on the end. But other than that, it's very similar. Number 14, again, in any log graph, you guys, the first thing you need to do is look at your product term, and that's x minus 1. And since the original graph has x, since x is the product term, and since we're replacing it with x minus 1 in this case, all right, that's why the x minus 1, just like the 3 minus x over here, was the product term, and we did the same thing there. We're replacing the x with x minus 1 from the basic graph, and so that is the thing that you set equal to the 5 numbers. What 5 numbers is it this time? Well, it's not these same 5 numbers over here because the base is 3 this time. So again, how does it work? What did we do over here again? We did 1/3 of the -2, 1/3 of the -1, 1/3 of the 0, and so on. So now we're going to do what? We're going to do 3 to the -2, 3 to the -1, 3 to the 0, 3 to the first, 3 to the second. Okay. 3 to the -2 is 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the first is 3. And 3 to the second is 9. So now we solve those. These are the old x values from the basic graph on the front of the worksheet where the product term was just x and not x minus 1. So let's figure out what these 5x values, these new x values are. Remember, you can, again, round this off if you want. This would be 0.1. If you add the 1 over, that would be 1.1. This is 0.3. Add the 1 over, you get 1.3. And then we get 2, 4, and 10. Okay. And now, what are the new y values? Again, it's going to be the same as the original exponents, just like it was over here, except for the plus 2. So see these 5 new y values here? Same thing, except for you add 2 to it, because in this problem there was no plus 2 on the end. Now there is. So that thing after the bracket tells you how this changes. It'll be exactly the same thing if there's nothing after the bracket, but otherwise, what do? We go -2 plus 2. All right. So we're going to incorporate the plus 2 into this here. So -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. And finally, 2 plus 2 is 4. All right, so those are the 5 points I want to graph here. Let me get started here. Notice that 10 is a little bit off the board, but as I've said before, as long as your shape is basically correct, you can neglect one of your 5 points normally. In other words, it's not worth it to change the entire scale of the graph just to incorporate 1 extra point in there. All right, if you're missing 2 or 3 extra points because you didn't change the scale, that's different. But if it's just 1, might as well keep the scale, the 1, 2, 3, 4, 5 scale, the same way. And so I'll leave this out, and I'll just graph the other 4 above it there. So 4, 3 is going to be right here. 2, 2 is right there. 1.1, 0. Or pardon me, 1.3, 1 is 1.3, 0 is right here, and then 1.1. I apologize, and that must have been why I was getting thrown off. I was reading it wrong there. Excuse me. It was 1.3, 1. I think I said that, and then I got away from it. Pardon me there. And there's 1.1, 0 though. But before you graph it, remember, you need that asymptote in there to make sure that it doesn't cross over it, but it just gets closer to it. So where is that asymptote? Again, the product term, you got to set the product term equal to 0 and solve that equation. So let's do that. If I add the 1 over to the other side, I get x equal to +1. That is your vertical asymptote right there. And so we put the vertical dotted line right there, like that. Okay. And now we're ready to graph it, and as you know, we need to do a banana shape on any log graph, and as you also know, since it's a banana shape, it's not going to suddenly turn back around once it starts to go down really fast right here. So it gets closer and closer to the vertical asymptote as it goes forever downward. Remember, it's got to be either forever down or forever up as it gets closer to that vertical asymptote, and it's got to be forever down. All right, because it can't suddenly turn back around. It wouldn't be a banana shape anymore. And that is number 14. Last one. What is my product term? Since this is a log graph, I got to look at that first. My product term is x minus 4. And so that means I'm going to do x minus 4 5 times. Like that. And what do we set that equal to so that we can get a so we can get our new x values? All right. Over here, what do we have? We have 1/3 to the -2, 1/3 to the -1, and so on. Here we had 3 to the -2, 3 to the -1, and so on. So now we're going to have, because the base is 6, we're going to have 6 to the -2. Which is 1 over 6 squared, 1 over 36 in other words. All right, that is going to be the the first one there. The next one's 6 to the negative 1, which is 1 over 6 to the first. The next one is going to be 6 to the 0, which is 1. And then 6 to the first. And finally, 6 to the second. What are my brand new x values if I solve for x right here by adding the 4 over to the other side on each of these 5 equations? I'm going to get, and by the way, please don't just round off to the nearest tenth this time. If you want to convert this to a fraction or a decimal again, that is going to be 0.3. Okay, 0.3. And so, pardon me, I said that wrong. 0.03. 0.03. If you round it off, it would be 0.0, and so then when you move over the 4, it would be exactly equal to 4. The problem with that, and saying that this is equal to 4 here, is because that would be right on the vertical asymptote, and we can't have that. And that's not a contradiction. It just means that when you round off, sometimes it lands on the vertical asymptote when it's really supposed to be just really, really close to it. And so that is 0.03. So if I add the 4 over, it's going to be 4.03. Again, that's just a reminder that it's not 4, but it's slightly next to 4. All right. So that's why I didn't want to round it off to just the nearest tenth there. It would have been 4.0, and it would have looked like it was right on the asymptote. So, so round off to the nearest hundredth if the nearest tenth ends up being something that's going to be exactly equal to the asymptote here, because it's so close to the asymptote already. In fact, I'll show that to you. I wasn't going to do that yet, but just to show you here, you can see here that if I set the product term equal to 0 and I solve it like I'm supposed to, x equal to 4 is the vertical asymptote, and that's why I was saying that. Okay, 1/6 is 0.2 approximately. So if I add the 4 over, that is 4.2. All right, and then the rest of these, if I add 4 over, I'm going to get 5, 10, and 40. Okay. And excuse me there, I got in the way there of my new y values there. I can just I could just move that down towards near the below that there. So I'll rewrite that here in a second, but first of all, let me do the new y values. What are they? Again, they are exactly the same as the original exponents you used to figure out the old x values. -2, -1, 0, 1, 2, but with the exception being that you've got to add 1 to that. Okay, just like we added 2 to those 5 numbers here. So if I add 1 to the original exponents, -2 plus 1, -1. -1 plus 1, 0. And then adding 0 plus 1, 1 plus 1, and finally 2 plus 1. And there is your brand new y values right there. Let's go ahead and plot these points here. Again, let me just make that additional note that I just erased, just so you have it there. X minus 4 equal to 0. That's how you figure out your vertical asymptote. And so therefore the new vertical asymptote is, or it's not new, it's the vertical asymptote, excuse me, is x equal to 4. All right, what I'm going to do here, because these numbers get really big, and not just 1 this time, but 2 of them, is I'm going to change the scale so that I can at least fit the 10 on there. You don't need, again, 40 is the really big one, so if you want to leave the biggest one out, like we did over here, that's okay. It'd be better not to leave more than 1 out, because then you're starting to, you don't want to have too few a number of points. All right, you want to have most of them on there. So let's change the scale here so we can get at least 4 out of the 5. So I'm going to do 2, 4, 6. All right, same thing on this as well, 2, 4, 6. Because the x values get kind of big as well. Based on that, where are these? And by the way, be very careful with your vertical asymptote, because I changed the scale, the vertical asymptote, and you can wait until after you plot the points before you put this on here, but I'm just going to do it now. You can do it either way. But it's on this mark here now because the scale changed. Okay, just be careful of that, to make sure you put it in the right place and remember that you change the scale. this right here, which is 0.03, pairs up with, oh, I'm sorry, I was looking at the wrong things. I need to look at these points here. Excuse me. Those are the old x values over there. So I've got 4.03 with -1. Where is that? That is really, really close to x equal to 4. So I'll just get it as close as I can get it without touching it. 4.2 comma 0, again, very close to 4. And then the y is 0. 5 comma 1 is, oh, sorry, that's not right. Again, see how easy it is to mess up when you change the scale. We're so used to the 5 being in its normal place. 5, 1 is right there because 5 is halfway between 4 and 6, and 1 is halfway between 0 and 2. So it's got to be that mark right in between, in the middle of that box there. Let me zoom in a little bit more. Okay, what else? 10 comma 2. 10 is right here now. Comma 2 is right there. And then that last one is like way, way, way out here off the thing. But like I said, you can neglect your point with the biggest numbers. That's fine. So it's going to be a banana shape. Can't touch the asymptote. Okay. Make sure it's smooth, though. All right. Just like most of the other graphs we've done. Most. All right. Not the absolute value graphs, but most of the other graphs we've done. It is smooth. Don't have it take any sharp turns or anything. And it looks like a banana shape. Okay. Pretty narrow looking banana shape. Doesn't have a whole lot of shape to it. All right. It looks almost like a T-square or something. It's something that's just like, it looks almost like it takes a full sharp turn. I know it's kind of hard to not do that. It just has a little bit more of a sharpness to it than the typical banana shape, but it is still a banana shape. And so there you go. Again, put arrows on both ends. Don't let it touch the vertical asymptote. If it just barely skims it like I was talking about in the previous section, that's okay. Just don't let it cross over it. Okay, so just to summarize these banana-shaped things, not only from the log graphs, but also these graphs from the previous section where you had the variable and the exponent. Again, we always have, the graph is always going to be going up on one end, and it's going to be going down on the other. One end will be steep, the other end will be flat, okay? Same thing here. One end is steep, the other one's flat. It's going up on one end and down on the other. All right, so you cannot allow the end that is flat to turn back around and go the same direction as this one is. Okay, that would be inaccurate. Same thing here as I told you in 4.2. You take the flat end, you don't allow that to loop back around and go back up the same direction that the steep end was going. All right, so don't let this go back up. Don't let the flat end to suddenly turn and go the same direction that the steep end was going. That's the point. Whether you, it doesn't matter what kind of banana shape you have, whether it's these ones from 4.2 with the variable and the exponent, or if it's the logarithm ones. Okay. Another thing as well is don't allow the steep end. Don't allow that to turn and go back the same direction that the flat end was going either. Okay, because if you did that, then it will violate the vertical line test and it won't even be a function anymore. And these are all functions that we're graphing. So don't allow this thing, as it gets closer to the vertical asymptote, don't allow that thing to loop back around like this. It'll violate the vertical line test. All right. And it's the same thing over here, all right? If you allow the steep end on this one to loop back around like this right here, then it also would violate the vertical line test. All right, so so just a summary there of some characteristics of all the different banana-shaped graphs. All right, so that concludes section 4.3. And as usual, let me know if you have any questions, and you have a good day. Take care.